In this series of 3 lectures, we will see how the ideas of topology, specifically on homology and Morse theory, come together to help define the notion of the size of a topological feature. In this first lecture, I will introduce the necessary terms required for discussing topological persistence. I will talk about birth and death of features and the lifetime of a topological feature. Next, I will talk about a visual representation of these birth-death pairs into a 2D diagram called the persistence diagram. I will finally talk about persistence-directed cancellations. Let's begin by getting some intuition. As usual, we will start with a one-dimensional function. So here is a one-dimensional function f, and what we see is a graph of this function. You can notice that this function has multiple minima and maxima. Let's consider a sweep over the domain of this function in increasing direction of function values. So this sweep corresponds to moving a line upwards, which is increasing direction of function value, and looking at the set of points where the graph intersects the line. So let's look at this particular line, and the intersections indicate the number of points of the pre-image. So the number of so-called ISO points. So this is f inverse at a particular value c. If this value here is c, then what we are seeing is that f inverse of c has 6 components. Now the question is it indeed 6 components? What if the function was sampled and this sampling led to noise? So here is a sampled noisy version of the function. You can easily see that the number of components need not be 6. It can be more, it can be less, depending on the kind of noise. So the question is, how can we reliably report the number of components even in the presence of noise? As you can see, the number of components was something that we have seen earlier is an important topological invariant, and we have seen algorithms to compute it for different topological spaces. Now here is a situation where we want to compute this topological invariant, but we are affected by noise in our input. Persistence allows us to handle this noise. Now let's look at this particular 1D example to gain intuition. How will we try and solve this issue of noise? A natural idea would be to somehow smooth the function. Unfortunately, this involves numerical computation, and we'll try to avoid that. Another way to look at this problem of reliably reporting the number of components is to say how many of these components at the value c, right, for f inverse c, are true components, and how many of them are reported as components just because of noise, right? Another way to think of this is as follows. Say I am given a interval with width or size p. How many of these components that I am reporting exist even after p time or within an interval of p time, right? So what this means is that I want to report only those components that are definitely going to live past the value of c, for at least p amount of time, right? Or in the direction of the function f. So we want to call these components as persistent components. So this is the origin of this term persistent. We would like to somehow define this notion of persistence and then report all persistent components at all values c. Now this seems like a hard problem because you don't want to do this computation at every point c on the y-axis. Now, is there a way to consolidate all the information about the various components so that we can answer this query efficiently? Or ignoring the question about algorithm for a moment, can we define a notion of persistent component? So let's continuing with the same example. Let's look at the sweep of the domain in upward direction and keep track of the various components. As I start the sweep from negative infinity, I see that there are no components initially, and I keep increasing the value c until I hit the first minimum, at which point I have a single component. So I term this as a birth event. At the minimum, a new component is born. So this is a birth event. I continue increasing the function value and sweep upwards until I hit the second minimum. So this corresponds to a second birth event. I color code this to indicate which component is born. So you have two components as of now that are alive. When I hit the third minimum, a third component is born. We continue, and next we hit one of the local maxima. And when we hit this local maximum, interestingly, the two components merge. The two components that were born at these two minima merge together into a single component. Now, instead of thinking about this as a merge event, I want to rather talk about this as a death event, where one of the components dies, and so that I have only one surviving component, and the surviving component is now shown here in brown. So as you can see, I killed the younger of the two components and I allowed the elder to live. This is called the elder rule. Not too great in terms of lifetime analogy, but as we will see that this elder rule allows us to very neatly capture the topological features. Let's move upwards as we go along the sweep. There was one surviving brown component, and then there is the other greenish brown component, which again merge at the next second maximum. Now here again the elder rule is applied. So the surviving component is the brown component. So as you can see that during this sweep we had various birth events, and these birth events were at the local minima, there were death events at maxima, at local maxima. Now each death event can be paired with a corresponding birth event, so which is natural here. So there was this birth paired with the corresponding death, and so on. And there is no pair for this birth event, and it continues forever. So there is one component that never dies, right? So during this process, what we have seen is that we have been able to pair the local maxima with the local minima based on who is the creator of a component and who is a destroyer of the component. So we have what we see here are two critical point pairs. Each pair represents a creation destruction pair, right? So essentially the lifetime of one component. So as a part of this exercise, we have seen that that there are these birth and death events. So there is a birth event that corresponds to the creation of a component, because this is a one-dimensional function. The only kind of cycles that we will have are the zero-dimensional cycles, hence components. So we talked about birth events, and then we saw when these components cease to exist. So these were the death events, and we saw that the death happens at the local maximum in this one-dimensional case, and we decided whom to kill based on the so-called elder rule. Now together what we have done essentially is to be able to assign a size to each of these components, and this size is given in terms of the function value, so in terms of the lifetime. So, and this lifetime is what we will call as persistence. So this persistence is associated with each component. So in this case, this component, and it lived from the time of this minimum to the time of this maximum. So its lifetime is called the persistence, and we will also call this the persistence of the two end point critical points. So we will use the term persistence to refer to this particular topological feature, the component, and persistence corresponding to the two critical points that define that particular component. Let's continue with this analysis by looking again at Morse functions, but now in 2D. Let's move to flatland, right, where we have two-dimensional functions, and we are going to look at isosurfaces. In fact, we are going to look at what are called sub-level sets, so the collection of all points below a function value, similar to what we did in the one-dimensional case. So we have now a function defined over a 2D domain, and we are going to sweep the domain in increasing order of function value or height, and as we sweep up, we hit the first minimum, and a component is born, similar to the 1D case. And what I'm showing here is the minimum M1 and the component that is born. So the blue region indicates all the points that are below a particular function value. As we sweep up, we hit a second local minimum m sub 2, and we are sweeping up the domain. So naturally the region around m1 is also swept up. So this is shown in the light blue. That this is yet another birth event. Now as we keep sweeping up, we hit a saddle. Now something interesting happens at the saddle. The two components that were created at n1 and m2 merge. Now, as before, we don't talk about this as a merge event, rather we talk about this as a death event. The component that was born at m2 is younger, so it gets killed. The elder rule applies, so the component at m1 survives. And the way we capture this is using the pair m sub 2, the creator, and s sub 1, the destroyer. So this is one of the persistence pair. We continue our sweep, and as we sweep up, something interesting happens. As we sweep up, there was a single component that again merged at S2, a saddle, but this saddle happens to be a creator. Unlike S1, which was a destroyer, S2 is a creator. It creates a cycle that you can see at the center here. So S2 is a creator. Now as we sweep up, we have two alive cycles, a 0 cycle, the component that is born at M1, and a 1 cycle that is born at S2. Now as we sweep up, we hit a local maximum at the center, capital M. This capital M plugs the cycle because it adds a boundary to the cycle, and hence destroys that cycle. So naturally we have another pair, S sub 2 M. So S sub 2 M is another persistence pair, but note that this is a bit different from the pair M sub 2 S1 because they are pairs that represent cycles in different dimensions, right? What we did was the same as in the 1D case. We again talked about birth events, death events, pairing the birth and death by considering a pair of critical points, considering the lifetime of the topological feature by looking at the difference in function value at the destroyer and the creator, and assigning it as the persistence of this critical point pair. One quick thing before we move on, if you know, let's look at the indices of these critical points that form the pairs. M sub 2 has index 0 and S sub 1 has index 1. Similarly, S sub 2 has index 1, capital M has index 2. If you notice, these indices differ by 1. Hope you find this interesting, right? We have seen this earlier in the context of the Morse-Smale complex. So this difference in index of 1 is not coincidental. It is indeed relevant. The topological feature or the cycle that was created at the minimum can be destroyed only by a saddle. And similarly, the one cycle that was created at a saddle can be destroyed only by a maximum. So again, we have seen how this notion of persistence is able to capture the lifetime of these various features. Now, what is a value of this persistence. In this terrain, the first pair M sub 2 S1 is able to capture the size of the hill that was or the valley, not a hill, the valley that was created at M2. Similarly, the pair S sub 2M is able to capture the size of the mountain that is kind of defined by S2. So the pairs are able to capture or represent the size of these cycles, and that is the role that persistence plays. Let's look at one of the key representations of persistence. Again, I will use the zero-dimensional example. We have a one-dimensional function, and we are talking about the zero-dimensional homology, so the number of components here. As we sweep up in increasing order of function values. In the y-axis, you see that the y-axis is mapped to the function value, and you see C sub 0 through C sub 6. These are the different critical points, including the boundary points. And P sub I, C sub I are the critical values, and P sub I are the critical points. X sub I are the points on the domain where corresponding to these critical points. Now we have one critical pair, which is P sub 3, P sub 4. So the component that was created at P sub 3 is destroyed at P sub 4. This is shown in black. So the lifetime of this feature is shown in black. And in the subfigure B, you see the lifetime of the various features. The creators are shown with filled endpoints, and the destructors are shown with empty or circles with unfilled endpoints. The figure C towards the right, the subfigure C, shows an alternate representation, and this is called the persistence diagram. Each critical point pair is plotted as a point on the XY plane on the first quadrant, where the x-axis corresponds to the birth time and the y-axis corresponds to the death time. So the x equal to y line, the diagonal, corresponds to all features that die at the same time that they are born. So naturally, all the relevant or the interesting critical point pairs will lie above the x equal to y line. So you can already locate the black point, which is at a particular height above the diagonal, and this height is the persistence of this critical point pair. Similarly, the magenta point has a higher persistence and is located here. The green and so on. There is one point, the orange, which is which never dies. That the component that is born at P sub 0 never dies. This is also shown within the persistence diagram as a point at infinity. For technical reasons, the persistence diagram also contains all the points on the diagonal. But what is important for us are the 4 points, the black, magenta, cyan, and the orange, which corresponds to the different critical point pairs, the different components during this that correspond to the level sets as we sweep up in increasing order of function value. So this representation, called the persistence diagram, focuses only on the zero-dimensional or the number of components. So this is called the zero-dimensional persistence diagram. The subfigure B in the middle shows the same information as intervals, and this is called as the zero-dimensional barcode, naturally, because it looks like a barcode. So to summarize, what we have seen today is that the cycles can be represented by so-called endpoints, which are the creators of the cycle and the destroyers, during a sweep of the domain of the function. We pair the creators with the destroyers, and the lifetime is recorded and is called the persistence, and this persistence is associated with the critical points corresponding to the creators and destroyers. This persistence can play a role in topology driven simplification of the function. More specifically, the critical point pair cancellation that helps simplify a Morse function and get a simpler or a smoother Morse function. So this is what we had seen in the earlier classes on Morse-Mail complex, where given a function f, we can obtain a smoother function g by cancelling a pair of critical points. Now what we are saying is that we can order the pair of critical points by looking at their persistence or lifetime. This indicates the effect that the cancellation is going to have on the function. So in today's class, we saw how persistence can be defined within the context of Morse functions, and specifically looking at the cycles that are created and destroyed during a sweep of the domain, and so the cycles correspond to the cycles the cycles that we are talking about. They correspond to the homology of the level sets or the sub-level sets. So the set of all points that lie below a particular function value, or rather, when we were doing the sweep, we were actually looking at f inverse of negative infinity up to a particular point C. So in the next class, we will see a different view of persistence, and then we will understand how these two views are merely views, two views of the same idea.